In this video, I'm going to be talking about infinite geometric series. This is a unique series. These are series that have a common ratio. Okay, and we'll look at some examples here shortly. But if it has a common ratio, there's something very interesting that happens. And I'm not going to derive this because we've derived this before, but if that common ratio is a value between -1 and 1, non-inclusive, it can't be 1 and it can't be -1, but if the ratio is between -1 and 1, then the infinite series a1r to the n is equal to a1 over 1 minus r. So this is one of the few series that will actually be able to come up with a sum and not just whether it converges or diverges. So let's look at what infinite geometric series look like. So there's this general structure, and as we look at examples, you'll get more comfortable with the structure. They don't always have to fit this structure, but let's start with this one. N equals 1, so my first term is 1/2. If I plug in 2, we get 1/4. If I plug in 3, we get 1/8, and so on. So if you notice, we're multiplying by 1/2 to get from term to term. So this is an infinite geometric series. Here, kind of looks the same, but notice the k and the 2 are in opposite positions, so let's look at what that does. If I plug in 1, we're going to have 1 over 1 squared, which is 1. If I plug in 2, we're going to have 1/2 squared. If I plug in 3, we'll have 1/3 squared, and so on. So there is no common ratio. I'd multiply this by 1/4 to get this one. I'd multiply by some fancy number to get to that one. So there is no common ratio, so this is not a geometric series. This one I can rewrite as 1 over e to the n. Remember, e is just a constant. If I plug in 1, we'll get 1 over e. If I plug in 2, we get 1 over e squared, e cubed, and so on. So when we're multiplying, you'd multiply this by 1 over e to get this, multiply this by 1 over e to get this. So we do have a common ratio. So this one is an infinite geometric series. So the key is we're going to be looking at a bunch of different examples. If the common ratio is equal to -1 to 1, we can evaluate the sum using a1 over 1 minus r. So you may start to recognize the structure of it in sigma notation, but for right now, I'm going to go ahead and write out a couple of terms so we can clearly see what our a1 is and, more importantly, what our common ratio is. So we'll go ahead and write out the first couple terms here. Okay, and this is infinite geometric with a common ratio of 1/5. My a1 also is 1/5. Okay, 1/5 is between -1 and 1, so I can use my sum formula, a1 over 1 minus r, to find the sum. Okay, so we get 1/5 over 4/5, which simplifies to 1/4. Okay, College Board likes these kind of questions because something like this is real simple. This, looks more mathy. But if we start generating some terms, when 1 is 1, our exponent is 0, so we just get 1. Plug in 1, we get e over pi, e over pi squared. So my ratio is e over pi. So the question becomes, is that less than 1? Well, e is about 2.718, and pi is about 3.14, so this is less than 1. So we can use our sum formula. Now you could probably expect this to be on a multiple choice portion where your answer may be presented this way, or it may be presented simplified where you'd have to get a common denominator and such. But for our purposes, we can leave it like that. All right, next example. This is really in that A1 times R to the N, or in this case to the K. If I plug in 0, we get 2, 6/5, 18 25ths. And I know I'm doing that quick, but you're just plugging in different numbers for that K. My common ratio is 3/5, which is less than 1, so we can find the sum. So we'll have A1, which is 2 over 1 minus 3/5. We'll go ahead and simplify this down a little bit. So we get 2 over 2/5, which is the same as 10 halves, which is 5. Okay, this next one looks really similar, but something will happen here. We're going to have 2. My next term, if I multiply 2 times 5, we get 10 thirds, 50 ninths. So my ratio is 5 thirds, and we can see the terms themselves are getting bigger, which means we can't have a sum, but just the fact that this number is bigger than 1 means there is no sum, also known as divergent. And on the multiple choice, what they would do is have some numbers, and likely one of the options would be series diverges or it's divergent. But it doesn't mean you can't plug in your 2 and your 5 thirds to get a value. It just doesn't have any meaning for this problem. Next one kind of looks similar, but presented in a slightly different way. So we'll be careful. So we'll plug in 0. So on the top, this will be 1. So we'll get a 6 over, this will be 1. If I plug in a 1, this is 2. So 9 times 2 is 18. On the bottom, we'll have 5 to the first. Plug in 2, we're going to get 54 over 25. So looking across the top, to get from 6 to 18 to 54, we're multiplying by 3. On the bottom, we're multiplying by 5. So my R is 3/5, which means we can find a sum. My A1 is 6. And then we'll get through this computation. So especially when it's written in a funny manner, it's helpful to write out those terms. Okay, our next example. Across the top, 3, 9, 27, 81. We're multiplying by 3. On the bottom, we're multiplying by 4. But notice that the signs are what we call alternating. I'm going plus, minus, which means my ratio is going to be a negative 3/4. Which is still between -1 and 1, so we can find a sum. And again, do some calculations. 3 over 4 over 7 over 4 is 3/7. Now sometimes College Board likes to disguise their series as geometric or not. So this looks complicated, but sine pi over 3 is just a value. It is our y value at pi over 3, which is root 3 over 2. Okay, if I plug in 0, we get 1. If I plug in 1, we get root 3 over 2, and so on, which is geometric. My A1 is 1. My R is root 3 over 2, which we may need to simplify, but if we look at our multiple choice as they're presented, that's what C looks like. Okay, this one here, says if f of x is the series from 0 to infinity of cosine squared to the k. Lots of parts here, but let's just break it down. Okay, if I were to expand out the sigma, we'd plug in a 0, which would give me 1. If I plug in 1, we'd get cosine squared x. If I plug in 2, we'd get cosine squared x squared. So this does happen to be an infinite geometric series where my ratio, what we're multiplying, is cosine squared x, which is kind of different, and we're going to see more of these types in later on. But I can go ahead and find a formula for f of x using a1 over 1 minus r. Nope. Okay, that would be my function. My last step then would be to evaluate this at 1. We just type this into a calculator, or it would have to be presented like this. Must be in radians. Everything in our calculus class is radians. You get 1.412. This last one is kind of a combination, but if both of these series converge, then we can add or subtract those values. Okay, this first one would be, I'm just going to do this all kind of separate. If I plug in 1, 2 to the 5th, or 2 fifths, 2 25ths, and so on. My r would be 1 5th. So that one would have a sum of 2 fifths over 1 minus 1 5th. Which is 2 over 4, or 1/2. Then I'm going to repeat this for this one, and then I'm going to go ahead and subtract the values. Here, if I plug in a 1, we're going to get a 0 here. So my first term is 3. My second term, if I plug in 2, we're going to have 3 halves, and so on. Which means my r in this case is 1/2. So we get 3 over 1 minus 1/2. 3 divided by 1/2 would be 6. So this is going to be 1/2 minus 6, which would be negative 11 halves. So that is your introduction to infinite geometric series and whether we can find the sum or not, and also if it converges or diverges.